Hello again. In this video, I'm going to go over the second part of section 2.3. If you remember in the last section, we evaluated limits using direct substitution. And those were cases where the limit of f of x as x approaches a is simply f evaluated at a. What we're going to do in this video is look at cases where this limit, the limit of f of x as x approaches a, is not equal to f of a, and therefore you cannot use direct substitution immediately to evaluate the limit. Okay, so what we're going to do in these cases where you cannot evaluate this limit by evaluating f at a is we're going to try to find an equivalent limit that can be evaluated using direct substitution. Okay, and I'll do an example of this, a couple of examples of this kind of case in a minute. But I just want to show you an example of what this particular case that we're looking at might look like. So here's a graph of a function. It happens to have a hole in it right here. And f evaluated at a is actually at this y value. But notice that the limit as x approaches a of f of x is actually this y value right here, which is below f of a. Now we know that because if you approach a from the right-hand side, you can see the y value is getting closer to this y value. Same thing if you approach from the left side, you can see that the y value is getting closer to this y value as well. So the limit of f of x as x approaches a is not f of a, right? It's this y value down here, which is not f of a. F of a, right, f evaluated at a is at this y value. So this is a case where you cannot use direct substitution to evaluate the limit. Okay, so let's look at a specific example, and I'll show you what we do in these cases to find the limit. Okay, so I'm going to look at both a and b here. Okay, so for part A, we want to find this limit. Okay, so the first thing you might try is to use direct substitution. But when you substitute 2 in to this, notice that you get 2 squared minus 6 times 2 plus 8 on top, which happens to be 0. And then on the bottom, you get 2 squared minus 4, which is also 0. Okay, so we're getting 0 divided by 0. And that is known as an indeterminate form. And what that means is, if you ever get this form of 0 divided by 0 when trying to evaluate a limit using direct substitution, what it means is we don't know what the limit is. And when we say that, we mean we don't know if it exists or if it doesn't exist. We have no idea. All we know is that in the current form that this function's in, we cannot evaluate this limit using direct substitution. So we have to do something else. So what we're going to do is we're going to try to find a different form of this function that's still equal to it. So we're going to try to simplify this. Generally what we need to do is cancel something. So we're going to find a simplified form of this function that's still equal to this function, and then we're going to try to evaluate the limit using direct substitution for that function. Okay, so let's see if we can't do that. So I think the key here is let's factor the top and the bottom. Okay, so this top piece factors into x minus 4, x minus 2. And the bottom piece factors into x plus 2, x minus 2. Okay, and these limits are still equal because all I did was factor. But now notice, these cancel, right? And so now you're left with this limit. And so now this function is still equal to the original function. But now when I try to evaluate this using direct substitution, I get -2 over +4. So -1/2. Okay, so the form that this was in originally, right? This was the original form of the function. This was an indeterminate form. Because when we use substitution, direct substitution, we got 0 over 0. And so that basically indicated to us that we had to simplify this. Like, look, generally speaking, you're looking for something to cancel. So you can simplify it to a different form so that when you do use direct substitution, you actually get a number. Or maybe it doesn't exist. Okay, in this case, it was a number. Okay, so this is the determinant form. And when I directly substituted in for 2, I actually got a number. And so this really is the limit. Okay, so if you were to like make a table for this and plug in numbers close to 2, like 1.9, 1.99, or 2.1, 2.01, you would find that the y values for this function are getting closer to -1/2. Okay, so let's try part B. Okay, so again, the first thing you might do to evaluate this limit is try direct substitution, but again, notice when you plug a 1 in, you get 0 divided by 0, okay, which is an indeterminate form. So this particular form that we have, we cannot use direct substitution to evaluate the limit. And so what we have to do is put it into a different form, one that is determinable. In other words, when we use direct substitution, we actually get either a number out or we get undefined out. Okay, so by the way, undefined is different than indeterminate. If you get something like 7 over 0 after you use direct substitution, that is considered undefined. Okay, as opposed to indeterminate. The reason is when you have a number approaching 0 divided by another number approaching 0, it is possible for this to actually get closer and closer to a number like -1/2. But if you have a number approaching 7 divided by another number that's approaching 0, then what's really happening is something like this. And if this continues to happen, just plug this into your calculator to convince yourself of this. This number is just going to blow up. The closer this gets to 7 divided by this other number that's getting closer to 0, the closer and closer those things get to 7 and 0, the closer this fraction gets to infinity. It just blows up and it becomes a really big number. So this heads towards infinity, okay, which means the limit is undefined or does not exist. Okay. Okay, so going back to this, when we plug 1 in, right, trying direct substitution, we get an indeterminate form. And so we're going to change the form so that it is determinable, so that when we use direct substitution, we actually either get a number out or we get undefined out. Okay, so here's the key in this case. What we're going to do is we're going to multiply this top piece by its conjugate. The conjugate would be square root of x plus 1. Now the idea behind the conjugate of this would be the same thing, but changing the sign in front of one of these two terms. And I'm going to change the sign in front of this, the 1, and make it a plus 1. So this is called the conjugate of this. Okay, now of course if I do that, I have to multiply the bottom by the same thing, because this has to equal 1. Otherwise I'm changing the value of the original function. Right? By multiplying it by 1, I'm not changing the value of it. I'm just changing the form. Now let's go ahead and see what happens here. When you FOIL this top part out, you get square root of x times the square root of x. which is just x. And then the square root of x times 1, so square root of x, and then the square root of x times -1. Okay, and then the last would be -1, right, times 1, -1. Okay, so first, outer, inner, last. That's what we get when we FOIL. And then you might be tempted to FOIL the bottom, but you really don't need to, so I'm not going to. Notice that these square root of x's cancel out, and you're just left with x minus 1 on the top, which of course cancels with the x minus 1 on the bottom, leaving you with a 1 on top. Okay, so the moment of cancellation is the key here. Once you get this cancellation, then it becomes a determinable form. And so now when I plug in 1 using direct substitution to evaluate this limit, I actually get a number. I get 1 over 2. Okay, and so that's what this limit is equal to. It's equal to 1/2. Okay, so just to kind of summarize what we've done here, these are two cases where you can't immediately use direct substitution, and we know that because we get an indeterminate form when we tried direct substitution. And so in both cases, we tried to change the form to a determinable form. In this case, we factored and canceled. In this case, we multiplied by the conjugate. And then after we FOILed the top out, we got that cancellation there. But in both cases, we changed it to another form, which was determinable. So in other words, when we used direct substitution to evaluate the limit, we actually either got a number or we got undefined. Okay, I hope you found this video helpful. Thank you for watching. Bye-bye.